Going back to linearizations for functions on one variable, I have a function y equals f of x, and I've sketched in its linearization. We call this standard linear approximation because for points near x naught, f of x and L of x look like the same thing. If I zoomed in, I'd have a hard time telling the function from its tangent line. Another way to say that is we can literally use L of x to approximate f of x. The other thing I can look at is a change in y. So I can imagine incrementing x just a little bit. So x naught plus delta x, the change in y, literally the difference into y values. So f of x naught plus delta x must be up here on the y-axis, and I see a very literal delta y, the change in those two, the difference in those two y values. The linearization gives me a way of approximating that change. And so that would be the change in the linearization. That's actually what we define to be a differential. That was our dy, which is equal to f prime of x dx. I should use an x naught there because I'm literally thinking about it being just at this value x naught. So delta y is also approximated by dy. And this is the actual change, right? Because delta x, dx I can think of as an independent variable that is equal to delta x. So if I increment by an amount delta x to find the amount that dy has changed, right? The amount y has changed on the linearization, that's just a matter of multiplying the change in x by the slope. And that's all this differential is really saying. And one of the neat things we see in one variable calculus is that a function is actually called differentiable when this is a good approximation. And so now the reasonable question is, what do I mean when I say when this is a good approximation? So the way this was written down, likely in your calculus course, is that delta y, right, the actual change in y could be expressed as f prime of x naught times delta x plus some epsilon times delta x. Your function was called differentiable if epsilon went to 0 when delta x went to 0. This literally saying that this approximation is a very good approximation when the amount we're allowed to go away from x naught gets smaller and smaller. We can use the linearization of functions on two variables to have the same kinds of ideas. So, if I imagine z equals f of x comma y, I can imagine its standard linear approximation, right? The equation of a tangent plane, but thought of as the linearization, so solve for z. Coming from this calculation, all right, so this is a z naught. This is my partial with respect to x evaluated at the point x naught, y naught. This is my partial with respect to y also evaluated at the point y naught. And then, well, this looks a lot like a change in x, and this looks like a lot like a change in y. And so if I think for a minute that this is really a z, and this is really a z naught, right, using the function to find that z value, giving it a name. Writing this back in this way, I start to see something that looks a lot like that definition of differential from Calc 1. right? This idea that there's some relationship like this going on. So this is literally a change in z. This is a change in x. And this is a change in y. And so in the same way, I define the differential dz to be the partial with respect to x evaluated at an appropriate point times dx plus the partial with respect to y times a change in y called dy. The corresponding change in y from Calc 1. Now this statement using partial derivatives. And again, dz can be used to approximate delta z. So imagine a surface and a tangent plane. Now my domain are points in the plane. And so I could imagine a literal change in x and a literal change in y. Going from this point to that point. It's not even in my domain. I should have done this a little more wisely. So I don't know, point there and there. So about there and there. Should have traced my circle and looked at the domain first. All right, and I see how the z changes, right? I see a delta x and I see a delta y, right? And I see the actual corresponding change in z, right? I'm at a high point and I'm at a lower point, and I could actually write down that delta z. And now I know I can use delta x as a dx, delta y as a dy to approximate the change in my tangent plane instead. And so, thinking about that as my original point, my tangent plane would look something like this, and my dz would be the difference from here to here. So the height doesn't drop quite as far to the sphere, but it would let me approximate delta z.